Mark your own now that I've completely wrecked Iron Man for you. Here we go. Oh, my favorite student. Oh, someone hasn't seen my favorite student yet. You might have to explain it to him, John, but we'll see. My favorite student. Her name is Ann Serkey. She gets everything right. He'll figure it out eventually. What is the definition of a force? What is the unit of force? So for 1 mark, if you said N, or if you wrote out the word newtons, that's the unit. What's the definition of a force? If you said a force is a push or a pull, I would live with that. Did anybody say anything else? You can holler it out and I'll say yay or nay. Probably yay. I think that was the official definition that I gave you on the first line of lesson 1, although I also said that's technically a bad definition because it's really a quantum, whatever. We're good enough. Oh, you could have said this, by the way. I would have lived with that because that's, a mass times an acceleration, that's a force. Fair enough. And then we started talking last day about this idea, Emma, of net force. Anytime I say the phrase net force, what I'm telling you is no free body diagram required. I've already done the winner minus loser for you. You can go straight to. So it's going to be 1,200 times 2. And I'm hoping many of you actually chose to do that one in your head without a calculator. It's the 2 times table. 2,400 newtons, 1 mark. Elias, how many marks is number 3 worth? 1 mark? Probably have to find something in order to find something, or maybe I might even have to find something in order to find something in order to find something if it's 3 marks. You kind of clued in, that's kind of how I cue you a little bit. Okay, just making sure. It says hint, find the acceleration. So they want me to find the force, and I should have said here the word net force. I've changed my quiz for next year, so if you fail my course and retake it again next year, you'll see it says what is the net force there. In other words, Calvin, I'm going to start by going F equals MA, and I'm going to notice I know M, it's 65. Do I know the acceleration? Not yet. So I walked over here and I went, okay, A equals question mark. It says it starts at rest, so I said VI equals 0. And this is some of the stuff that you were away for that you're going to kind of have to pick up between the cracks or watch all the video lessons that I recommended to you, Allie. VF is 770. 770 meters per second, that's more than twice the speed of sound. This is moving. And then it said it did that acceleration in 1.5 meters. 1.5 meters is about this distance here, roughly. It's going from 0 to twice the speed of sound in that distance here. Am I expecting a big acceleration or a small acceleration? I think I'm expecting a pretty significantly big acceleration. I'm not going to be getting like 15. I think this is going to be probably in the thousands, maybe in the hundreds of thousands, might even be in the millions. So I'm going to use VF squared equals VI squared plus 2AD. Everything from before Christmas is still fair game, and I will put some questions like this on your test because it's also good review. A is going to be the VF squared drops down like a domino, minus VI squared all over 2D. We're going to get 770 squared minus 0 squared all over 2 times 1.5. Is this a fraction? Is there more than one thing on the top? Brackets around the top. Although, does the minus 0 squared make any difference at all, Jack? Fine, I'm going to skip that. Divided by, definitely need brackets around the bottom. Or I could have gone 2 times 1.5 is 3. And I got that for an acceleration. I'm going to write 197,633 because I'm using this to find my next answer, so I don't want to round off. In fact, I'm going to use my answer button if I can. So 197,633 meters per second squared. And now I can walk over here and I can go F equals 65. I'm going to write 197,633, but you all know I'm going to use my answer button. The net force is going to be 65 times answer button. Y'all get 1, 2, 8, 4. Boy, that's big. I think I'm going to write this in scientific notation. This is about the time when it's less work to write it in scientific notation. If you didn't, you would have 1, 2, well that. I'm going to go 1.28 times 10 to the 1, 2, 3, 4, 5, 6, 7. That's how much force was applied to this 65 kilogram mass. 65 kilograms is around 150 pounds, so about the size of a person. This would be the human cannonball from hell, because this is going really, really fast. But this is also why artillery shells do so much damage, because that's roughly, it would lose some velocity to air resistance because it's going so fast, but that's pretty much how much force it's going to apply on the other end of its target when it comes to a stop. Artillery shells do damage. If you got that, 3 out of 3. Otherwise, I would probably do something like this. I would give you a half mark if I saw that. I would probably give you a half mark if I saw that. I would give you a half mark if I saw you got the A by itself. I would give you a half mark for finding A. That's 2 marks. Then I would give you a half mark for the numbers over here and a half mark for the answer. If you got A wrong, made a typo, but you took that answer and you went 65 times that answer, I would give you 1.5 out of 3. I would at least say, hey, you did most of it right. Hey, how many marks, Elias, is number 4 worth? What do they want me to find? No, they don't. What do they want me to find? They said net force, and I'm going to use F equals MA. In fact, I went like, oh, change colors, Mr. Dueck. I went like this. I rewrote it in my head because it's a pretty easy one to rewrite. And I said, well, that's going to be 12 divided by 1.2. And then I did that in my head as well. I said, is the correct answer 10 meters per second squared? Is it? I think it is. So almost exactly 1G. Not quite. Honestly, close enough that if you were that person or that object, you probably wouldn't notice a difference. You would think, yeah, it's 1G. Number 5. Good yawn? Good stretch? That's okay. We're bringing it. They want the average acceleration. I looked at the data they gave me and I said, I don't think I'm finding acceleration from force. I see VI is 0. I see VF is 3.2 times 10 to the 4th. And I see a time of 32 seconds. I think I'm going to use VF equals VI plus AT, but Kyla, I'm going to get the A by itself. It's going to be VF minus VI over T. I got 3.2 times 10 to the 4th minus 0 all over 32. And then I said, hey, I got a 3.2 on the top and a 32 on the bottom. I bet you I can do this in my head as well. Is the answer 1,000? Is it exactly 1,000, I think? Yes? Question, Sarah? Are you okay? Oh, okay. 1 mark. What do they want me to find in B? Now you can say your line. Net force. Yeah, there you go. So now I want F equals MA. I would feel okay giving you a question like number 5 on the test card and not walking you through part A, just asking part B and expecting you to clue in, I don't know, the oh, he gave me enough to find the acceleration. Is that all right? So what was the mass? 4.5. Jeez. Come on. 4.5 times 10 to the 4th times 1,000, which is going to be 4.5 times 10 to the 7th newtons, or a 4, a 5, and 6 zeros if you wrote it out the long way. I just added the 3 zeros to the exponent. It's got to be 10 to the 7th. Yes, I think. Hope I haven't made a silly mistake. Cool. Now they want a distance. I said, okay, D equals question mark. Once again, I saw from rest. VF is 12. You know, if I could find the acceleration, I think I could do this, because I think I could use VF squared equals VI squared plus 2AD. I think I could go with D equals VF squared minus VI squared all over 2A. So I went over here and I said, okay, A equals F over m. Force is 1.6, 6.4. Mr. Dueck, why did you say 1.6 newtons east? I just stuck a direction in there because when I was typing this, it just kind of popped into my head. Okay. Do you get an acceleration of 0.25? I think yes. No? Yes? Good. Now I'll walk it over to here. So it's going to be 12 squared minus 0 squared all over 2 times 0.25. I can do that in my head. It's going to be 12 squared. It's going to be 144 divided by 0.5. Is it 288? Meters. If you got that, 2 out of 2. Otherwise, I would probably give you a half mark for that, half mark for the answer, half mark for that, and a half mark for the acceleration. So remember before Christmas, I was often telling you, Kyla, try not to use an answer to find an answer. You know what? We've been doing pretty good. We've been doing some physics. Now I'm saying go ahead. If it's easier to use an answer to find an answer, as long as you're certain you did that answer right, take the shortcut and just do it. Now they want me to find time. I think I'm going to go T equals VF minus VI over A. VF equals VI plus AT, and I rewrote it. It's going to be 12 minus 0 all over 0.25, which 48 seconds, yes? 2 marks for that, so I would probably go something like, you know what, I'd probably go 1 mark for that, half mark for the numbers, and a half mark for the answer. That's a really messy 5, even more messy than normal. Turn the page. A book is sitting on a level desk. I looked at the binder in front of me. Which of the following statements are true? A, true or false, there are no forces acting on the book since it's not accelerating. Does that mean there's no forces? That's false. It means the forces are balanced, and since I know gravity's acting, that's how we were able to reason the table, the normal force must exist. Newton's first. The magnitude of the normal force between the book and the desk equals the magnitude of the gravitational force. I agree with that. The net force on the book is equal to 0. Is it accelerating? Then the net force is equal to 0. True. Friction is what's holding the book on the desk. I don't think so, because I think your desk could be made of ice, and as long as it was level, it would still stay there. So the number 7 is false, false. Number 8. This is a job for a Freebody diagram. Now, how did I figure that out so fast? First of all, there's a scale which implies a normal force west, and there's definitely gravity. I got more than one force. There's a tug of war going on. I better do a Freebody diagram. Do you have to? Some people get good enough to do this and go straight to the equation, but I won't help you if you have a question if you haven't done the Freebody diagram. And, I mean, how often do you get to draw in high school for marks? So, you know, yay. Gravity. We're accelerating up, so I know that's winning. So my equation is winner minus loser equals MA. What if I gave you the normal force and I said find the acceleration? How would you get the A by itself? I don't know what that means. I think it meant something, but yeah, okay, divide the M. As far as I'm concerned, I can either give you the acceleration and say find the normal force, or I can give you the normal force and say find the acceleration, or later on, I'll give you the normal force and the acceleration, and I'll say find the person's mass. That's a bit trickier because how many M's are there in this equation? How many would you prefer to have? 1. What do I do if there's 2? I'll show you a clever Math 9 trick, which will also come in handy in your Math 11 courses. Plus that over. You know what, Mr. Dueck, let's show work just so you can give up part marks. The normal force is going to be MA plus MG, so it's going to be M. I don't know M. Or do I? First of all, please don't say M is 588 kilograms. That's well over 1,000 pounds. This elevator is not going to be working too well if somebody that large is sitting in it. Just saying. How can I figure out the mass from that 588 newtons? Wes. And you know what? I'm so lazy, I'm actually just going to write here 588 divided by 9.8. I'm going to do it right in my calculations, and then I'm not having to round off or anything. A is 1.2 plus, oh, and I can just write 588 because that is mg. So 588, whoop, one too many eights, times 1.2 divided by 9.8 plus 588, 660 newtons. If you got that 2 out of 2, otherwise I would give you 1 mark for that equation, half mark for that equation, and a half mark for the answer. Now we're accelerating downwards. I wonder if I can just in my mind modify this free body diagram here. If we're accelerating downwards, which line would be longer in this free body diagram here? Who would be winning? Same answer. And so I'm going to have this mg minus the normal force equals ma. I want to get the normal force by itself. We called this the swappy dance. I'm going to plus the Fn to that side. At the same time, I'm going to minus the ma to that side. And I'm going to get normal force equals mg minus ma. It's going to be 588 minus m, 588 over 9.8 times a, 2.25. Mr. Dueck, we're accelerating down. Shouldn't that 2.25 be negative? Psst, it is. Winner minus loser took care of whatever I needed. 588 minus 588 times 2.25 divided by 9.8. You get 453? These are all working out evenly. Well, that's rather nice. Newtons. Same as before. 1 mark for that. Half mark for that. Half mark for the answer. Elevator moves up at a constant. Ooh. Here, I would still have gravity down. I would still have normal force up. Will the normal force be bigger, smaller, or the same size as mg? In fact, it's a tie. I can say the normal force equals mg, which means it's going to just be 588 newtons. Ta-da. 1 mark, 1 mark. What if the elevator rope snaps and we're accelerating downwards at 9.8 meters per second squared in free fall? What will the normal force be? Yep. If you showed work, fine, but you just said, I know it's 0 because I've wrapped my brain around the physics, that's good as well. 2 marks. Can you give yourself a lovely score, please, out of 23? If you need to lawyer with me, now is the time. Otherwise, you're going to pass the quizzes inwards towards the center. Person in the middle is going to put them in a nice, neat stack, all facing the same way. Everybody right now, put your pen or pencil down. With your writing hand, press it against your lab table flat, like this. Pull towards yourself when you're pressing flat. Can you feel something resisting you in the other direction? Do it again, but press harder. Pull towards yourself. Did that force that you feel resisting you get bigger or smaller or stay the same? This force is called friction. It's a really tricky force. We're going to look at it at a higher level, diving down into what exactly is going down between the electrons and the protons and the atoms. There is still some debate over exactly what's going on there, believe it or not. So we're going to look at it, we'll be able to calculate it, but if you want a good explanation, I'll give you an okay explanation that's technically probably wrong, as I've been doing most of the year. So here is my explanation of what friction is. It's due to the interlocking of molecular hills and valleys between a surface and an object on the surface. Your lab tables may look smooth, but if you were to zoom in, you would see that on an atomic level, they're bumpy. And so as two surfaces go across each other, those bumps catch on each other and hook on each other and apply a resistive force. Yeah? Rolling is different. The first answer is if an object is rolling, there's no friction, none. See why in about 2 minutes. It's a good question. But basically, if I had a completely flat surface and I had a bowling ball and you rolled it, the reason the bowling ball stops is almost entirely air resistance, not friction. Key idea with friction, you can underline this, it resists sliding. If you're trying to figure out the direction of the friction force, that way. Because of that, it can resist motion, like when you're trying to slide on a heavy object across the floor. It can also create motion for walking and for rolling and for cars. So, example 1 says, draw the direction of friction in each case. If we're sliding a block to the right now, these notes were typed in a very, very old version of Word, and I can no longer edit the graphics. Yours might look like there's a tiny gap between the block and the surface. That shouldn't be there. It's on the surface, so I'm just going to kind of color that in. For what it's worth, I have to be nitpicky. What direction is this block sliding? To the right? Friction will resist that motion relative to the surface. So which way is friction going to be pointing? To the left or to the right, Kyla? Yep. My abbreviation for friction is F and then an FR. I don't know why I put the R there. This is one of the few times when I write an extra unnecessary letter, because I'm pretty sure F with a subscripted F would be enough to tell you that it's friction, but for some reason I started putting the R there when I started teaching, and I can't break the habit. It's one of about the only time my laziness does more work than normal. Car speeding up. How can friction push a car forwards? Well, if you follow the tires, what direction are the tires trying to move relative to the road when the car is going forwards? The tires are trying to move backwards. The direction of motion of the tires is backwards. Friction resists motion, and so that's why friction for a car tire when you're accelerating is going to push forwards. When you hit the brakes, if you're hitting the brakes, your car tires are trying to push forwards against the surface. Friction resists that motion, and that's why when you hit the brakes, now friction will act that way. Put your pencils down, look up. Sarah, here's your answer. Friction only occurs when there's a difference in velocities between the two surfaces. If a ball is rolling, that's terrible. Let's try a little better. Pretend that's a circle. Shut up. If a ball is rolling right there, the relative velocity of the ball and the surface are identical because the ball is moving forwards and we can pretend that the surface is just plucking along. So when an object is rolling, there is no friction. I didn't know that actually until about 8 or 9 years ago. I used to always say, oh, friction is what brings the bowling ball to a stop. And I had another physics teacher say, Calvin, you haven't thought about it well enough. There is no relative motion between the ball and the surface once it gets going. So it's not friction, it's almost all air resistance. Hashtag nerd trivia, or next page over. What does friction depend on? If your desk was made of ice, and I had you put your pencil down and press your hand against there, would the force that you felt resisting you be bigger or smaller or the same as if your desks are made of the current countertop? So one thing friction depends on is stickiness, or slipperiness, depending on whether you want to look in one direction or the other. So the type of surfaces that are in contact and how slippery or sticky they are in relation to each other. Stickiness has a symbol and a name. It's called the coefficient of friction. A higher coefficient of friction means these surfaces are more sticky. A lower coefficient of friction, closer to 0, these surfaces are more slippery. Car tires, for example, on pavement have a coefficient of friction of around 0.7, 0.65, 0.75. Closer to 1 is really sticky. Bigger than 1, it'll be like glue. Oh, now we're beyond friction. Something's really sticky. Okay? We have a symbol for the coefficient of friction. It's the Greek letter mu. And as a symbol, it's this. If you look up, I'll do a big one. You know what? Here's a mu right here. It's sort of like a lowercase u with a big front tail. It's actually where our letter M, our lowercase m, comes from. You can kind of see a handwritten lowercase m kind of hidden in there. So it's boom, like that. There's all sorts of jokes because for this Greek letter, what does a Greek cow say? Mew. What does a Greek, whatever, right? What does a Greek cat say? Meow. But this is the symbol for stickiness. It doesn't have any units. It's not a force. It's just a ratio. It doesn't have any dimensions, no units. But if mu is large, lots of friction, we would say sticky. If mu is small, not much friction, we would say slippery. So steel on ice has a mu of about 0.01. Rubber on concrete has a mu of about 0.75. What else does friction depend on? Well, is it easier to slide a lightweight object across the floor or a really heavy object across the floor? Lightweight. And so at first it might be, maybe it's mg, but do you remember how I had you press down harder and friction got bigger? Okay. I'm going to stand up and walk away from the microphone and then use your table. So if I want to pull this, I have to overcome friction. And if there was more, if the table was heavier, friction would go up. But I also want to take into account that if I lift up as I pull, friction is way less. I don't have to pull anywhere near as hard. And I also want to take into account that if I push down as I push forwards, I was pushing that way as hard as I could, but I was also pushing down. Friction got bigger when I pushed down and lighter when I lifted up. So I don't think I want to use mg. I think what I want to use is how hard the ground has to push back up to counteract the force down. That's why when you push down, which force were you making bigger when you pushed down in your free body diagram? The normal force. A much better way to calculate friction. So I wrote here, friction depends on the force pushing the surfaces together. In basic problems, that would be mg. Get the obvious one, normal force would be the same size. But that doesn't allow me to explain why pushing down on something or lifting up on something changes the friction force. And so a much better measure would be the normal force. Here it is, your last equation of the unit. Friction is equal to mu times the normal force. You'll probably end up memorizing that one because you get sick of looking it up, but it is on your sheet. Mr. Dueck, how do we find the normal force? Free body diagram. I already told you I don't have an equation for the normal force. So often, almost always with friction, I'm doing a free body diagram. Okay? Friction depends on how sticky the objects are and how hard they're being pressed together. Yeah, that makes sense. By the way, that's why grease or oil, what it does is it lowers the mu, it lowers the stickiness to reduce friction. That's why if you're trying to slide heavy furniture across the floor, you lift up as you slide. There you're changing the normal force to reduce friction. Example 2. Suppose we were pulling on a 6.5 kilogram, suppose we were pulling a 6.5 kilogram mass across a rough surface with a mu, with a stickiness coefficient, with a coefficient of friction of 0.64 at a constant, you know what? I should underline the word constant speed. How hard do we need to pull? I don't know. I want a number. First of all, what's it asking me to find? How hard I'm pulling on this thing here. You know what? This is a job for a free body diagram. Although, did they give me a picture? I'm going to label the picture. What are the forces acting on it? Get the obvious one. Go systematically. What's the first force we're going to put on here? Everybody, let's label mg. Is this box sinking into the ground like quicksand? Is it flying into you like Superman? So what force am I missing right now? There has to be an arrow pointing up, the same size as mg. Which force is that? Okay. It wants us to figure out how hard we're pulling, so I'm going to go like this, and I'm going to call it F, I don't know, pull. Why must that diagram be wrong? Why can't that be correct? Why must there be friction? Yeah? Why isn't it accelerating? What's telling you that? So constant speed means the forces are, I'm looking for it means letter B. Balance. So not only do I know, Sarah, that there's friction, I'm going to draw that arrow the same size as I drew my F pull arrow. Eyeball it. In other words, I wouldn't do that, and I wouldn't do that. And I would take mark, if I'd asked you to draw the free body diagram, I would take marks off if you did any of those. So about like that. What does it want me to find, Karn? F pull. We're going to write an equation for the horizontal forces. Now, normally I would say, who's winning? And then I would say, who's losing? But Emma has already said, because we're not accelerating, it is a tie. Yes? So I think I can say that. Can I not? By the way, we'll extend it to when we're accelerating as well. It's not that much tougher, but yes? Okay. It wants me to find F pull. I can't find F pull, but what I can find is friction, which must be the same size as F pull. What's my new equation? Friction is what times what? It's in the box right up there. I've scrolled down. Mu times the normal force. And so whenever I say friction is what times what, your response can be mu times the normal force. So I'm going to say mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What force is the same size as the normal force in this particular free body diagram? You see the little three-step conclusion chain we made there, Allie? We said, I can't find F pull, but I know it's the same size as friction, so I'll find that friction is mu times the normal force. I don't know the normal force. But I know it has to be the same size as mg, so I'll just put those numbers in. That'll give me the right answer. What's mu? I don't know. What's mu with you? What's mu? 0.65? I've scrolled down. What's the mass? I hope I gave you a mass. 6? G, 9.8, not negative or anything like that. We're just using its magnitude to calculate how big the normal force has to be, to calculate how big friction has to be, to calculate how big the pulling force has to be. 0.65 times 6 times 9.8. You all get 38.22 newtons. Pull harder, this will accelerate. Pull less, and this thing won't move at all because you haven't overcome friction. Oh, 0.64? Sorry, I heard these numbers. 6.5. Yeah, it'll make a huge difference. And 0.64, I heard wrong numbers from you, sorry. Let's try that completely again. 0.64 times 6.5 times 9.8. How about 40.768? Yes, no, yes? I'll go to 3 sig figs, 40.8 newtons. We are often going to have a mystery force coming from off the page, like F pull. We're going to give that mystery force a special name. So if we have an unknown force coming from off the page, turn the page, if we have an unknown force coming from off the page, we often just call it the applied force. And my symbol for that is F applied. What I mean by that is something's tugging on the rope. It could be invisible little leprechauns or angels or somebody else. I don't care. All I know is something's applying a force off the page. I'm not going to make up a story every time to tell you where it's coming from. I'm just going to say it's coming from off the page somewhere. Example 3, I like example 3, I like example 3, I like example 3. Suppose we are pulling on a 6.5 kilogram mass across a rough surface with a mu of 0.64 with an applied force of 86 newtons. What's the acceleration of this mass? Ooh. Ah. Curtis, what's this question asking me to find? I know I caught you zoning out. I know my audience. Good. Good recovery. If you hadn't done that sigh, we would not have noticed. You could have totally covered it up. You could have pretended you're paying attention the entire time. You got to get a poker face, my friend. The poker face. Okay. What's what you find? I don't see a VI, a VF, a time, or a D. You know what? I'm finding acceleration with forces, especially since I see another force in the equation. In fact, this is a job for a free body diagram. What are the forces acting on this? Get the obvious one. Is this mass sinking into the ground like quicksand? Is it flying to like Superman? I know there is a normal force. We're pulling with an applied force. Boy, I drew that badly. Let's try that again, Mr. Dueck. F applied. Is there friction? How do I know? Anytime I say rough surface or give you a coefficient of friction, that's me saying you better include friction. Now here's the question. My friction arrow, which way is it going to point? Is it going to be bigger, smaller, or the same size as F applied? How do I know it has to be smaller? Are forces balanced this time? How do you know they're not balanced? Curtis, what am I asking you to find? If they were balanced, what would the acceleration be as a number exactly with no math right now? So, I'm pretty sure friction this time is smaller. I'll exaggerate it so it catches my eye. You okay with that, Jack? Okay. Vertically, the forces are balanced, but I'm going to write a horizontal. I want the horizontal acceleration, so I'm going to write a horizontal force equation. Who's winning? Who's the loser? Oh, Karn, you didn't see. I said, who's the loser? And Wes looked at you. Oh, okay, fine, Wes. Who's the losing force? Yeah. What does winner minus loser always equal, Wes? Stop. What am I trying to get by itself, Curtis? You know what? You can all write MA, but then my first step would be, what am I trying to get? What am I trying to find? You know what? I would do that right away because I'm lazy. In fact, honestly, I probably wouldn't have written the M and crossed it out. I would have just written equals A and divided the M over because I've done that so many times. Alrighty, here we go. So A is going to be F applied. I know F applied, it says it's 86. Just lifted that right from the question. Minus friction. Friction is what times what? Why, that's mu times the normal force, our new friction equation. All over 6.5. What's mu? I don't know. What's mu with you? What's mu? 0.64? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? Yeah. Right around now, students start to think to themselves, oh, friction is mu mg. It is not. I'm giving you basic normal force questions right now, but I'm going to add other up and down forces later. So don't ever say to me, friction is mu mg. I'll snap in a nice loving teacher kind of a way. Friction is mu times the normal force. I don't know the normal force, but I can figure it out from my free body diagram. So I can say here, A equals 86 minus mu mg all over 6.5. 86 minus mu was 0.64. M was 6.5. G is 9.8. All over 6.5. I would strongly encourage all of you to be comfortable typing that into your calculator. Believe it or not, we're going to get far more complicated than that in a few days. So, is that a fraction? Brackets around the top. Don't need brackets around the bottom. Oh, unless you have your fancy two-level calculator fraction, then you can just use your fraction button, which is also fine. I have no idea what the answer is here. You're not one in your head, Mr. Dueck? Yeah, no. What'd you get, Sarah? Oh, your calculator isn't working. Can I give you a loaner? Because it's important that you practice typing some of these in. You tell me, cat. Sorry, Wes, what'd you get? Ryder or Karn? 6.95, anybody else? I see some nods. Is it 6.95 rounded off properly, or did it work out even? I don't think it would have worked out evenly. 6.95, what? So is it 6.95 or 6.96? So that's what you said the first time, right? Right. Units, it's an acceleration. Meters per second squared. Okay. Now we're building. So if you tell me how sticky the floor is and how heavy the object is and how hard I'm pulling, I can tell you what it's going to accelerate at. We can go even further than that. Suppose we're pulling a mass across a rough surface with a force of 48 newtons. What's the acceleration? Curtis, what does this want me to find? You know what this is a good job for? Gravity. Normal force. F applied. Friction. Mr. Dueck, isn't this the same question? I don't know. Who's winning? Karn, do me a favor. Look to your right at Wes. Who's the loser, Karn? There you go. Sorry, who's the losing force? Equals MA divided by M. So I'm going to get a really similar equation to the one that we just did. It's going to be F applied minus mu times the normal force all over M. I'm going to get F applied, which was 48, minus mu, which is 0.64. Oh, I don't know the normal force. Oh, but look. I don't know the force is the same size as the normal force. Which force is the same size as the normal force? So I'm going to put mg right there over m. So it's going to end up being 48 minus 0.64 times 6.5 times 9.8 all over 6.5. I think you're going to get a weird answer. I think. Maybe not. Do you get a strange answer at all? Or am I totally wrong? Sorry? Positive? Is it 1.1? It's positive? Anybody else? I don't know. I got to try it. You know what, Mr. Dueck? Let's do it up here because I think some. So bracket 48 takeaway 0.64 times 6.5 times 9.8. Close off the top divided by. Do I need a bracket on the bottom? No. Oh, 1.11? Okay. Double check. Typo, right? I stand corrected. I thought there was a chance we might have got a negative answer. If you're ever finding A and you get a negative answer, here's what that means. You picked the wrong winner. The other force is the winner. But it's actually a fairly easy fix. All I would do is I would say, that's positive because it's a winner. That's negative because it's a loser. And I would continue that all the way through the question, making my winners losers, negative, and my losers winner, positive, and then just retype it. Yeah, I figured you would eventually. How much more am I getting through, Mr. Dueck? Okay. I'm going to pause here. I am going to start to assign some homework, but I'm going to give you more homework next class, and I'm going to also finish off friction next class. But if you're looking to get started, ooh, whose phone was that? Everyone's looking at Sky right now. Was that Sky's phone? Are we getting Timbits from you? Oh, thank you. That is so gracious. You know, it would be great if that was your brother texting during Mr. Dueck's class. That would be iconic. If he'd managed to sort of from a beyond get Timbits, that would be great. Anyways, you can try number 1. You can try number 2. So number 1 is asking you to find A. Number 2 is asking you to find the applied force, constant speed. We did that one. Number 3 is asking you to find mu. So do your free body diagram, when you're wanting to get your equation. Try and get the mu by itself. How would I do that? It's up to mu. That's, oh, so, okay. I'll just temporarily try those 3 for now.